Black holes, a region of space where matter is packed so tightly that it generates an incredibly powerful gravitational force from which nothing can ever escape, not even light. But wait, if light cannot escape it, it means that you cannot see a black hole. And if you can't see it, how can you be sure that it even exists? Well, we know they're real because we can feel and detect their presence, even if we cannot see them directly. You must understand one thing about black holes. They aren't an ad hoc explanation for some inexplicable astrophysical phenomena we encountered in space. In their case, the theory came before the observation. In fact, much before. It was the year 1916, and Carl Schwarzschild followed the field equations from Einstein's groundbreaking general theory of relativity to their most extreme conclusion. What he discovered was absolutely astounding. An object so compact and massive that it warped the very space and time around it so severely that nothing, not even light, could escape it. You see, it was a monster born from pure mathematics, not vivid imagination. Despite this strong foundation, black holes remained little more than a theoretical curiosity for decades. It was only in 1964 that the first black hole candidate Cygnus X1 was discovered, and its identity wasn't even confirmed until the 1970s. Over the years, physicists have predicted countless bizarre, perplexing, and counterintuitive behaviors that these objects should exhibit. And as our instruments became more powerful, we continued to confirm those behaviors through observations. In fact, we now rely on these behaviors to identify black holes and verify their existence. Today, you will see how it's done. The most powerful evidence of a black hole is its gravitational influence. Sure, it is invisible, but its gravitational effects? They are impossible to miss. You see, wherever a black hole exists, everything around it behaves weirdly. And you don't have to look far to see this in action. Let's take a peek at the center of our galaxy. What you see here is S2, a star that's barreling at an incomprehensible speed of 7,650 kilometers per second. That's almost 3% of the speed of light. Another nearby star has been observed to be hurtling at a jaw-dropping speed of 24,000 kilometers per second, which is about 8% of the speed of light. These staggering speeds aren't even the most fascinating aspect about these stars. It's what they are orbiting. Using orbital physics, we can calculate how massive this object in the center must be. The math doesn't lie. This monster of an object, named Sagittarius A, packs as much mass as 4.3 million suns. With so much mass, it should be burning with enough brilliance to outshine an entire galaxy. But guess what? It's totally invisible. What's even more surprising is that it's incredibly small too. Despite its ridiculously large mass, Sagittarius A has a relatively tiny radius of 12 million kilometers. To give you some perspective, if we could somehow stack together 4.3 million suns into a ball, it would fill up a volume 835 times bigger than what Sagittarius A currently occupies. It's another thing that the present-day universe doesn't let stars more massive than 150 to 250 solar masses to exist. So it's not like Sagittarius A can be a regular star either. The only object we know of that can compress so much mass into so little volume is a black hole. Another telltale sign of a black hole lurking in the dark is gravitational lensing, a beautiful, cosmic optical illusion. Einstein's general theory of relativity combines space and time into a unified quantity called the space-time continuum. And gravity isn't a simple force that pulls things together like we intuitively know it to be. It's a curvature in this space-time continuum, a sort of warp. Every object with mass, from pebbles to planets, warps the space-time around it. The greater the object's mass, the more pronounced this distortion is. And this has a fascinating effect on light. Although light always travels in a straight line, it appears to bend around massive objects. What's happening here is that it's just following the straightest line possible in what is essentially a curved space. It's like you walking from one point to another on the Earth's surface. You may walk in a straight line for 100 kilometers, never changing your direction. But the Earth's surface itself is curved, making your travel along this straight line a curved path. And this apparent bending of light makes it look like it has passed through a lens of some kind. It distorts the images we receive. Massive objects like galaxies and supermassive black holes distort the space around them so much that things behind them can appear stretched, arced, magnified, and even multiplied into several ghostly images. When galaxies act as cosmic lenses, you can see them glowing brightly at the center of the rings. However, when black holes cause the lensing effect, there's nothing in the center, just a dark, invisible void. That's when you know it's a black hole. Although galaxies made up of almost or entirely dark matter can cause similar distortions with nothing visible in the center, astrophysicists can look at other pieces of evidence to ascertain the identity of the object causing the lensing, and one of them is X-rays. That's because X-rays aren't easily created in nature, especially in abundance. Ordinary matter only needs to heat up to a few thousand kelvins to produce visible light, but X-rays are radiated by matter blazing at millions of kelvins. That's several thousand times the surface temperature of the sun. In other words, not a lot of things can make X-rays. They are much rarer than most other types of radiation like radio waves or visible light. Black holes are among the few sources of X-rays. But wait, a black hole doesn't let any light escape. So, how could it be emitting X-rays? Well, it's not. Not technically. You see, they are not usually loners. In most cases, they exist in binary systems with a companion star. In the case of supermassive black holes, they are surrounded by a lot of interstellar gas. And thanks to their powerful gravitational influence, they end up pulling and devouring matter from nearby sources like a companion star or interstellar gas. This infalling matter rarely dives straight into this dense object. Because of its angular momentum, it spirals into it, forming what's known as an accretion disk around it. As it spirals into the gravity well, it accelerates to extraordinary speeds, approaching the speed of light as it gets closer to the event horizon. Here, it collides, compresses, and heats up to incredible temperatures as high as 100 million kelvins in some cases. That's about 7 times hotter than the sun's core, hot enough to radiate extremely high-energy X-ray particles. In some cases, black holes can accelerate plasma matter to high energies and speeds, producing powerful polar jets. If these jets are drawing power directly from the rotating black hole and not its accretion disk, they can even emit gamma rays, besides X-rays. So you see, X-rays are emitted by matter just outside this dark object's event horizon, not from inside it. But there's a problem. Black holes aren't the only objects in space to emit X-rays. However, what's really fascinating about X-rays is that each type of X-ray source has a unique signature, a sort of X-ray fingerprint. By mapping those fingerprints, astrophysicists can determine whether it is a black hole, a neutron star, a supernova, or some other object emitting the X-rays. Besides jets, black holes provide another compelling piece of evidence for their existence. Gamma-ray bursts. Think of gamma-ray bursts as the supercharged versions of black hole jets. They are far, far more powerful. But unlike gamma-ray jets that can last for millions of years, gamma-ray bursts are short-lived. In fact, they usually last only a few seconds at most, but in those few seconds, black holes can release as much energy as a star does over its entire lifetime. It's no exaggeration that gamma-ray bursts are the most energetic explosions in the known universe. And it's no surprise that these unfathomably violent forces of nature have equally violent triggers, such as the birth of a stellar mass black hole or the cataclysmic merger of neutron stars. Gamma-ray bursts are also generated during neutron-star black hole mergers and during tidal disruption events when entire stars are shredded. Depending on the type of event causing them, the gamma-ray bursts can last anywhere between a few milliseconds to hours. The best thing about them? Gamma-ray bursts are incredibly common. Orbital satellites discover a new gamma-ray burst almost every day, and experts estimate that 50 times more GRBs go undetected. The only limitation here is our ability to detect them. GRBs are so powerful that we can detect black holes located billions of light years away. But it is only recently that we really developed the technology to detect one of the most direct pieces of evidence proving the existence of black holes, gravitational waves. Einstein had predicted their behavior as far back as 1916. He had theorized that certain kinds of motion, such as accelerating objects, would generate ripples across the space-time continuum, and they would travel at the speed of light, stretching and squeezing the very space-time in their path. Generally, these gravitational waves would be too minuscule to be detected. However, extreme events like black hole mergers release a tremendous amount of energy in the form of gravitational waves, which are relatively easier to detect. You see, black holes locked in orbits around each other end up spiraling inward and experience extraordinary acceleration in the process. This fast and rapidly accelerating cosmic dance of the two massive bodies generates powerful gravitational waves, which grow in intensity with each spiral until they hit their peak at the instant of the merger. That's the moment of creation of some of the most powerful gravitational waves ever witnessed, and these ripples in space-time travel across the universe. After the merger, the newly formed black hole emits a signature ringdown, a sort of fading gravitational wave signal that rings like a big gravitational bell across the universe. All of these theoretical predictions were finally verified in 2015 when the LIGO Observatory detected gravitational waves from the merger of two black holes about 1.4 billion light-years away. One of the black holes had 36 solar masses, and the other had 29. Their merger should have created a black hole with 65 solar masses, but something extraordinary happened. The merged black hole only had 62 solar masses. So, what happened to 3 suns' worth of missing mass? Well, the merger event was so cataclysmic that the missing mass worth 3 suns was converted entirely into energy in the form of gravitational waves. In the last 20 milliseconds of the merger, these black holes released 50 times more energy than all the light released by all the stars in the entire observable universe. And these weren't even particularly big black holes either. Since then, LIGO, Virgo, and CAGRA projects have detected dozens of other mergers involving black holes and neutron stars. Although neutron star mergers can also produce gravitational waves, they have their own unique signature that allows astrophysicists to determine whether the objects involved in the merger were black holes, neutron stars, or both. The unfathomable influence of black holes on our universe and the objects within it is undeniable. Although we cannot see them, touch them, land on them, or study them up close, their influence is so strong and powerful that it literally ripples across the universe. Despite their freaky physics and weird behaviors, black holes are an astrophysical inevitability and an inescapable reality. They push the boundaries of physics to the extreme and hide some of the best-kept secrets about the nature of the universe. And we may never uncover all of them. If that makes you think of them as unreal, that's fine. It's only natural. If you loved exploring the nature of black holes with us today, make sure to hit that like button, share, and subscribe to our channel. Turn on the notifications. It will motivate us to create more exciting videos on universe and its mysteries. We're just getting started,